All right, let's continue analyzing combinations. Here is one problem that I vividly remember. I assigned it one on the exam, thinking that it's kind of straightforward to do it, and the response was very, very bad. It was a killer. No, sometimes it's not the way we see it, you know, so the general student view are sometimes different. So they don't see that main start, and then later on everything is easy. So what is this? We want to count how many bead strings of length 10 contain exactly 3 ones. Yes? Exactly. So yes. So how many 10-digit binary numbers have exactly 3 ones and 7 zeros? So here the question is there, and we want to interpret it as something that's one of the configurations that we studied. Do you agree? And here is what I saw very often, something that confused people, and that was they said, is the order important? The order is important because these are digits. So how do you shuffle digits? That is important. Don't you agree? So people say, aha, order is important. These must be permutations. That's how they were trained. But actually, you have to be careful when you call these, you know, general patterns. Which order do you have in mind? So I agree, order of digits is important, but our job here is not to shuffle the digits. What is our job? We have 10 spots, do you agree? Yes. And then what's our only job in our design? To choose 3 spots where we will put ones. Once I choose that, I'll put ones there, zeros on. So the question here is, choose 3 spots out of 10, yes.
So the problem was, if you did use a permutation, you'd be differentiating between 2 or 3 of the 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, zeros, like the order of the ones within themselves versus just filling up 3 spots of 1.
Exactly. So shuffling, so those 3 are ones. If you shuffle them, does that matter? No. So the only thing that matters is choose 3 spots. Let's say like this. If I choose 4, and then I choose 7, and then I choose 10, will that determine my number, yes or no? Yeah. But what if I choose 10 first, and then I choose 4, and then I choose 7? Will that give me the same number, yes or no? So what matters is which 3 places you choose, but not in which order you choose them. Do you agree? Order of digits is important, but not order of which way were digits chosen. So generally what? The whole assignment, so let me write a little bit on the board. Example 434. Count 10-digit binary numbers with exactly 3 ones. 3 ones. Or maybe better, 3 ones. This is better probably. If you want to see that digit. And then what? This whole problem actually says, take 10 digits and choose 3 where you want to put your ones. Which order do you choose them? Doesn't matter. Once you choose them, you'll put your ones there. And then it's easy, what? 10, 9, 8. Over 3 times 2, you cancel here, so it's 120. That's it, nothing big. So message from this problem is, don't rush that order important or not. In how many distinguishable ways can we reorder the letters of the word hullabaloo? What's happening? First time in this chapter, we are allowing repetitions. So far, when we did permutation, when we did R permutations, when we did combinations, we always, without emphasizing it, we always say no repetition. So once you are chosen as a member of the team, you cannot be chosen again, of course. So here, first time, we have actually some letters that are being repeated. So what happens in this case? All right. So how many letters is this altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you agree? So however I shuffle it, I have 10 digits to fill in. So here are 4 places. I mean 10 places. I just do them 2 by 2 so it is easier to count. So how can we organize the count? Let's say the following. Let's do it one thing. So there are 2 different ways to see this. At the end of the story, we'll have a formula, but I want to do design, and actually that kind of explains why is formula working. Who is the trickiest here? I would say letter L. Why? It's repeated 3 times. Do you agree? So what? Let's choose where do we host L. L's. So let's choose, like in the previous problem, among these 10 spots, I need to choose which 3 will host L's. Do you agree? And then order between L's doesn't matter, so each of them occupies a place. So host L's in how many ways? 10, choose 3. If there are 3 L's among those 10, I will choose to host L's. Am I done with my word, or I just started my word? I started, that means don't add up later on whatever I do. What do we do? Multiply. If you have stages, then the count for the stages is multiplied. So imagine that I did my 3 L's wherever, all kinds of options, let's say here. What do you want to do next? How many spots are left? 7. And on those 7, you want to choose, is there anyone else who's repeated? A's and O's. So A's, I need to choose for A's what? There are 7 left. I need to choose 2. Now what? There are 5 left. I need to choose 2 to host my O's. And then H, U, and B, then that's easy what? Shuffle them however you want, which is what? No, 3 of them, 3 factorial. There are 3 of them for 3 remaining places, no restrictions, times 3 factorial. Do you agree with me? Let me simplify this calculation. It's this. 10 factorial over 7 factorial times 3 factorial. Do you agree with that formula? Is that what 10 choose 3 is? But then, next one exactly starts at 7 factorial. And then it goes what? 2 factorial times 5 factorial. But that 5 is exactly what next one starts. 5 factorial over 2 factorial times 3 factorial. And then last one starts with 3 factorial. So what happens? Cancel 7 factorial with 7 factorials. Those n minus r's all cancel. So formula actually says what? 10 factorial over 3 factorial times 2 factorial times 2 factorial. So what happened at the end? Did I just do regular 10 factorial? Why am I dividing? For the repeats. Why? Because those 3, when I shuffle them, they were counted, but they are the same. So that's why I divide by 3 factorial, because shuffling between L's shouldn't count, because when I shuffle them, I get 6 different versions of the same thing. If I put different colors on my L's, you will see I counted them as 6, but they're only 1. That's why I divide by 3 factorial. Why am I dividing by 2 factorial? Because of the double shuffling for O's, and then double shuffling for A. So basically, it kind of makes sense even not to go this way, the way we did it, just to remember the formula. And here is the formula. Formula says what? I hope I have it somewhere. Here it is. 432 says, suppose a collection of n objects consists of k types of objects where the types have n1, n2, nk repetitions, where n equals n1 plus nk. The number of distinguishable permutations is n factorial, and then you divide by the repeats. Of course, the way the theorem was formulated, 1 repeats are also counted, but what do we do for them? Do we do 1 factorial on the bottom all the time? But they don't. So we don't write those 1 factorials. So here is something to use when you do the counting. So once again, this is an extra formula to remember. If you have permutations where some objects are being repeated, then there is a way to count those permutations, and formula hopefully makes sense. And that's basically the main part for today. In the second part of the lecture, we want to talk about properties of combinations. They have some very nice properties and interesting. And actually those properties will be used on Monday when we start talking about binomial theorem and many other things. So I'd like us to learn these properties and also to be able to prove them. Sometimes I rarely ask proofs of the theorems from class to be proved, to be presented on exams. But for these properties, I often ask them because they show nicely if you have techniques of work with combinations. So what are those properties of combinations? First few are fairly trivial. So what is, sorry, I skipped those trivial ones, obviously. First one is very important one. If you remember, when I was doing some calculation, here someone says, yes, you cancel that, but you can also cancel 4. You remember that? Someone says from the front row, you can cancel 4s. Actually, if I knew this theorem at that time, I could have predicted that. So before I give you the proof, let me tell you what is the importance of this theorem. Suppose, again, the whole course I keep warning you, examples are not proofs, but usually here I give you examples instead of proofs. But I'm clearly emphasizing that these are not proofs, but it should give us the idea why is this so useful and important. So here it is. Let's say I need to calculate the 19 choose 16. What's special here? You see how 16 is very close to 19. That R is quite big. Then what? The way I explain it to you to calculate it, I'll do this. 16 times 15 times 14 times 13 times 12, 3, 2, 1. And here I said now do 16 numbers, takes forever. Do you agree? And tons of them will still be canceled. So what this tells you is the following. 19 choose 16 is the same as 19 choose 3. Why 3? Because that's complement from 16 to 19. It's 19 choose 3. And that's what it says. N choose R is the same as N choose N minus R. And that's very convenient sometimes. What is the reason? So let me give you the proof. First, give you an idea here. Very often these properties have both modeling reasons as well as algebraic reasons. What is the modeling reason? I have 19 people. And I need to choose 16 to go to be members of the committee. Can I do an easier job than that? Instead of choosing which 16 will be on the committee, what can I do? Which 3 will not be on the committee, and whenever I tell you which 3 are not, all the others are. Is that the same count, basically, yes or no? or 3 on anti-committee or whatever it is, but the count is the same, and that's why it makes sense. So that's why this is true modeling-wise, but let me give you the, what is the proof algebraically. So proof, so theorem, n choose r equals n choose n minus r. So what's the proof? N choose r, by definition, this is n factorial over what? Subtract and then repeat your r. But what is n choose n minus r? Subtract and then list. But when you subtract n minus r, what do you get? R. So you get n factorial over r factorial n minus r. Did I get the same thing, basically? Just with a different order. This and this is the same thing. So just from definition, it goes directly. So generally what? Whenever your lower number exceeds half of the top one, it's better to go for a complement. It makes your calculation easier. Next property that we want to prove. Oh yeah, these are two easy ones. They are just in the example. What are they telling us? On the extremes, how much is n choose n and how much is n choose 0? If you choose everybody to be on the committee, in how many ways can you do it? One. That's common sense. How about calculation-wise? Can we do it calculationally? Let's see. N choose n equals n factorial over what? N factorial when you subtract first. 0 factorial times n factorial. But how much is 0 factorial?
1.
So we get altogether what? 1. How about n choose 0? Are they complementary? So it's also 1. How about n choose n minus 1? What's complementary for n choose? N choose what? In how many ways can you choose one member out of n? N ways. So this is it. And before I show you the next property, which is the most famous property about combinations, let me start something that you all probably saw. Let me do n equals 1, n equals 2, n equals 3, n equals 4. Yes?
Is it an error if the second number is bigger?
Here?
The n choose n plus 1?
Yes, it is, because you can formally write it, but generally you cannot choose 8 members out of 7. You know, that's contradictory, because modeling it would be contradictory. And then if you can play with it, you know, if you are interested in that formally algebraic object. All right. Let's see if we have n equals 1. If you have one object, exactly following the comment of your colleague, if I have one object, what are the only questions that make sense? If I choose what? What are my options? Either choose what? Nobody or 1. So 1 choose 0 is 1, and 1 choose 1 is also 1 that we saw a minute ago. If I have 2 persons, what can I do then? I can choose nobody, which will give me 1, or I can choose 1 person, which will give me what? Or I can choose 2 persons, which will give me what? 1. All right. For 3, we can get the same thing. 3 choose 0, which is 1. And then I will stop writing, or I'll just calculate them. So 2 choose 1, 2 choose 2. This is just 1, this is just 1. What's say?
It's Pascal triangle.
Exactly. That's what Pascal triangle is. Pascal triangle gives you all the choose values for different values of n. So when n equals 3, but you need to write it half a space to the left. So 3 choose 1 is here. So what is 3 choose 1? 3. 3 choose 2 is the same because of the symmetry, which is 3. And then 3 choose 3 is 1. So for 4, the same thing. You start with 1 always. Then 4 choose 1 is 4. 4 choose 2 is what? 6 when you calculate it. Because of the symmetry, we get 4. Here we get 1. So what do we notice so far? This is famous Pascal triangle. And what happens there? First, there is 1. When there is nobody, then what? You only have what in the middle? 1. And I will erase all this. Here are the numbers. So here is another 1. I erase this to keep the symmetry. So here is that Pascal triangle. In every row, you actually have listed all the possible choices for that row. Is that clear? But there is one more property that's very famous about Pascal triangle. And what is that property? The property says the following. I can actually, even without doing any choices, get the next line for n equals 5. How can I do it? I add 4 and 1, I get 5. I get 4 and 6, I get 10. 6 and 4 to get 10 in the middle. Here is 5, and then I put 1s on the side, and I immediately get n equals 5 values. So why is that working so? So what is happening here, actually? Let's see what happened here. I took this, and I took this, and I went on the next line. So what was that? What is this 4 standing for? It's 4 choose 1, do you agree? And plus, this stands for 4 choose 2. And I got what? 4 or 5 now? 5 choose what? 1 or 2? 2. So what happened like from this example? Can you guess actually property of Pascal triangle? What is that property telling you? That when I choose 2 consecutive, and it looks like this, if I choose nk, and then I choose the next one, which is an r, maybe we call it r usually, r plus 1, who do I get? On the next level, n plus 1, r plus 1. That's a famous property of, we call those binomial coefficients for the reason you will see on Monday, but that's the famous property of choices. When you add 2 consecutive choices, you get 1 single choose on the next level, but at the higher r. And that's our next theorem. Although in the formulation of the theorem, I wrote it 1 level before. So I didn't call them r and r plus 1. How did I call them? R minus 1 and r, which is the same thing. So let's prove this theorem. Theorem. N choose r plus n choose r minus 1 is n plus 1 choose r. If you take 2 consecutive choices, or binomial coefficients, that's how we call them, then you will get the coefficient on the next level with the higher r. For which r's is this true? Be careful, we are subtracting, so we cannot use this for r equals 0. The lowest r we can use is what? R equals 1. R is between 1 and what? And n is fine. All right, how do we prove that? Don't think of doing it by induction, because this is exactly what we are trying to prove, how they behave from one level to another. So that's what you will use if you want to use induction on them. But first time you have to pay the price, and it's not bad. So what is it? Well, let me do the left side. N choose r plus n choose r minus 1. I asked this a couple of times on the exam so that people show me that they know the definition and they know the property, and and that can handle those. So do we know definition for n choose r? Yes or no? What would that be? N factorial over n minus r factorial times r factorial. Plus, on the second one it will be n factorial over n minus r minus 1 factorial. So I subtracted them carefully, putting second one in parentheses, times r minus 1 factorial. And this is fairly easy, but you have to do it once so that you don't get messed up with all these big expressions. What's one thing? If you want, you don't have to do it, but if you want, do they both have n factorial, yes or no? Don't be tempted to cancel it. So that n factorial has to be preserved because I need n plus 1 factorial. So don't do anything with this one. Just keep it. If you want, I can factor it out to protect it from bad ideas. But what can I do here? I just want common denominator. Unfortunately, they are close, but they are not the same. So what's the idea? Whoever starts earlier, pull out one member. So these two are easy to see. Who is here? Actually, you know what I'll do?
1 factorial over r equals r minus 1 factorial.
So yes, so do you see that I will need r factorial on the right side? Do you see that? So why don't I build r factorial? I like this, but this guy is a little short. So how do I make it nicer? Multiply both top and the bottom by what? R. So I'll multiply by r here and by r here. So what do I have so far? I have n factorial over n minus r factorial times r factorial plus n factorial times, let me put it in the protection. What would that be? Let me distribute this minus. N minus r plus 1 factorial times r factorial. And then the same thing. Is this guy a little short of this? Yes or no? Who's big? Yes. Plus 1, because it was r minus 1, but that minus distributes on the minus makes it plus. So who's bigger, n minus r or n minus r plus 1? So this one has a little longer sequence, so this guy is a little short, do you agree? What is it short by? Yes, so I'll multiply by n minus r plus 1 up and down. And this guy is just waiting. So what did I accomplish? That was our plan. Can I write this now as a single factorial, yes or no? It got that extra member, so where does it start now, this factorial? Starts not with n minus r, starts with what, n minus? Yes, because it got that first highest member. So what would that be? N minus r plus 1 times n factorial over n minus r plus 1 factorial times r factorial plus n factorial times r over n minus r plus 1 factorial times r factorial. Actually, we're almost done. What is the good news here? Do they have the same denominator? So we'll copy that common denominator. Although I will write it a little differently. Looks like n minus r plus 1. I will write it as n plus 1 minus r factor. Is that the same thing? Add 1 after subtraction or before is the same thing. You'll see in a moment why. Over r factorial. What do I do on top? Do they both have that protected n factorial? I'll factor it out, so who's left? n minus r plus 1 and plus r. So what happens? R and R are canceled. So who did I get on top? N factorial with an extra n plus 1 in front of it. So does it continue nicely? So what would it be?
Plus 1 factorial.
N plus 1 factorial over n plus 1 minus r factorial times, what is this? Do we recognize who's this? Is this a choose definition? Who's on top? N plus 1, choose what? R. Because here is n plus 1 factorial, subtract them, put factorial, bottom factorial, that's it. And that's your right side, yes?
What happened to the n minus r term in the, where you have the little bracket?
Here, it got absorbed here, like 8 times 7 factorial equals 8 factorial. Because this is exactly before n minus r.
Sorry.
Yeah, so then on the next one, they build the next factorial.
It just becomes part of the
Yes, the way I wrote it is like, something, really polished so that you do minimum of calculations, but you need to know where to do what. So there are much simpler, much less elegant, but more natural ways to handle it, but it's all together. It's just that build that common denominator somehow. And it's not much more than that. So that's why this formula, look at the title after the theorem, it says what? This is exactly what? Pascal's formula, and that's the formula that actually establishes the work of Pascal triangle. So when you do, once again, let me write it from the beginning. You write triangle of ones for a good reason, and then what do? Next member, but that half a space is exactly to push it to the right. So you get 2 here, and then ones on the side in your triangle. Again, add these 2, that's 3. On the second spot, but a little shifted, because 1 is here, so there is a little translation. 2 and 1 is also 3. 1 is here. 1, 4, 6, 4, 1. 1, 5. 10, 10, 5, 1, and so on. So that's how this goes. By the way, if you can also look at it this way, these are n choose 1s, these are n choose 2, these are n choose 3. So there are many different and nice ways to look at the Pascal triangle. Yes?
Go from the last step, so n plus 1 factorial over...
N plus 1 minus r.
Okay.
From this to this?
Yeah.
By definition, because it says k choose r equals k factorial, k minus r factorial. So I just did that with n plus 1. But maybe a little finesse, not finesse, but you see here it says n minus r plus 1. In order to see it like that, I push that 1 ahead so that it really matches the description. All right, one interesting, so here is that Pascal triangle. Here is one very interesting problem. I think this one is also from Ebb's book. Very often there are many identities with coefficients of the Pascal triangle, and they are proved in all kinds of different ways. So what this says is what? n choose 0 squared. So what is that doing? It says the following. If you go into one line of Pascal triangle, like this line, and you square all of them, what are you going to get? Middle member on the Pascal triangle twice deeper in the Pascal. So square each of them, add them up, you will get a single member twice further down the road in the Pascal triangle. Why would that be true? So, now since we know how they behave when n go from n to n plus 1, you might be tempted to try proved by induction. And sometimes they really work by induction. But this example has a very nice modeling solution that's very elegant and quick. So you do it just in one move. What is it? Suppose, so you just generally make them two stories that give you the same result, and one matches the left description, one matches the right description. So, suppose I have n stars and n squares. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So n stars and n squares. Let us count all committees of n objects. So I have n stars, n squares. I want to choose n objects. Is this a good idea? No. Why? Because if I call them stars, I don't distinguish between them. Let me distinguish between them. A, B, C, so that I know who is who. Star 1, star... Yeah, I can label them. Star 1, star 2, star 3, star n. And the square 1, square 2, and square n. So that I distinguish. It's not like which star I got, have no idea. Then what? If I make a committee of n, in how many ways can I do it? How many objects do I have? 2n. How many do I choose? n. So what's the total count? It's 2n over n. Do you agree with me? Is this the total count? So 2n choose n. So in here, I have 10 of those objects. If I need to choose 5, in how many ways can I do it? 10 choose 5. Make sense? Now I'll say the following. Let me do a little analysis and kind of classify all these committees. On those committees, so what? So let us count them all together. Now let us distinguish. Let us distinguish according to the number of squares and stars. So what? Case 1. All stars. In how many ways can I choose if I want all stars? So what? If n, in n case. So I choose n for stars, and n choose 0 for the squares. Do you agree? What if I want one star? No, all but one. All but one. All but one are stars. Then in how many ways can I choose those n minus 1 stars? N choose n minus 1. And in how many ways can I choose this one square? In what? Do I multiply? Because they are pieces of the committee. And so on. At the end, what will happen? I will have what? N choose 0 times what? N choose n. When I add them up, should I get 2n choose n? Yes or no? So what did I get? I got the following. N times n times n choose 0 plus n choose 1 and n minus 1 plus n choose n choose 0 equals 2n choose n. Unfortunately, that's not what we needed to prove. I need squares. Can I trade this n choose n for n choose 0? Because of the symmetry. So this is also n choose 0, n choose 0. So I always trade the left one. I didn't write them nicely. And 0 first. 0 first and second. So I trade the right one for the left one. So here it will be n1, choose what, times what? n1, and then nn, nn equals 2nn. Here it is. Here are your squares. So it is really true. So what is it? I like this problem a lot because it shows how good modeling can save you from heavy induction or heavy algebra or anything. This is so elegant and simple. Generally, it just looks a little bit like Halmosh problem, you know. Different way of counting. So you have counting by stage or counting by assigning losers. The same thing here. You had counting in total or on stages, and those two give you actually connection between two formulas about coefficients.
Was this the reason why the triangle, Pascal's triangle was made, or was there lots of reasons that they all worked